Today we're going to start the third and final module of the class, which is Gödel's theorem. It is, I think, the coolest development in mathematical logic in the past century. It's this incredibly fruitful result, so it's used for a bunch of things. The proof is extraordinarily beautiful and easy for such an important result. And as you'll see, it has an air of paradox. So there's something weird and unsettling about the theorem. So sometimes one hears the theorem stated as something like, if you have a sufficiently interesting piece of mathematics, then there's no way to axiomatize it so that you get both consistency and completeness. So in other words, if your axiom system is consistent, then it's going to be incomplete. There are going to be things that are true about your chunk of mathematics that are not going to be entailed by your axioms. But the way I think of the theorem is just as a point about complexity. So just as the observation that mathematical truth, even of a pretty basic mathematical theory like arithmetic, is so complex that it can't really be captured by any axiom system that finite beings like ourselves would be in a position to grasp. So really what we're going to do is we're going to talk about complexity. So this week we're going to talk about Turing machines. And I'm just going to talk about the usual things one talks about when one talks about Turing machines, and in particular the busy beaver function. And you guys will see that when we show that the busy beaver function is not Turing computable, that will basically be a dry run for Gödel's theorem. So if you guys get that, like, you'll be all set. Proving Gödel's theorem will be super easy. So bear with me. We're going to do a lot of talking about Turing machines and computability. Fortunately, that's something which is super fun. Of course, if there's anyone here who's course 6, you may know this stuff already. So sorry about that. OK, so let me tell you what a Turing machine is. A Turing machine is an especially simple kind of computer. This is how simple it is. The computer consists of a paper tape, which we can assume to be infinite in both directions. Maybe there's an assistant who's ready with extra stocks of paper. So if you're about to run out, the assistant adds more paper onto it. And it's divided into cells. And then the machine has a tape reader, which is positioned at all times at some particular cell. So here I'm going to indicate it with an arrow. And what the reader can do is it can detect when symbol is written on the cell where it's sitting. And it can erase that symbol and write down a new symbol. And it can move around one step at a time. And if you want to program a Turing machine, then what you do is you have each line of code have the following form. So each line is going to say, if you're in this current state and you're reading current symbol, then write new symbol and walk one step in this direction, which could be a null direction, and go to this state. So this presupposes that the machine is always in some state or other. And states are just natural numbers. So one assumes that a Turing machine always starts in state 0, and then its state changes as the machine does things and applies command lines. So here's an example of a command line. So say that there is an A printed on that cell. Then there might be a command line that says, if you're in state 0 and you're reading an A, then write down an X, advance one stage to the right, and go to state 7. So then what happens is the reader's there. It looks for a command line that tells it what to do if it's in state 0 and reading an A. It finds this one, and in a properly written code, there should only be one command line that starts with a 0 and an A. And then says, OK, so replace the A with an X. Move one step to the right. And go to state 0. Sorry, state 7. And what it's going to do next is it's going to look for a command line that starts 7 blank, meaning if you're in state 7 and see a blank, then do blah, blah. That's it. That is all there is to Turing machines. The fact that they're so simple means two things. First, it means that programming anything interesting on a Turing machine is an extraordinary pain. So if you actually want to program things, you should not use Turing machine. You should use like C++ or Python or whatever. But because Turing machines are so simple, if what you want to do is not do programming, but understand general facts about computers, if you want to theorize about computers, then this is your beast. And the reason it's fun to theorize about these things is because there is this amazing thing that you can prove. You can prove that anything that can be done on an ordinary computer can be done on a Turing machine. So if you prove, for example, that no Turing machine could possibly compute a certain function, then that means that no ordinary computer could compute that function. Indeed, even if your ordinary computer had limitless supplies of time and memory. And because it's so easy to prove things about Turing machines, it might be easy to prove that that function is not computable on a Turing machine, and therefore that is not computable on an ordinary computer. So it's very cool. In fact, most computer scientists believe that something stronger is true. They believe that it's not just that the things that can be done with a Turing machine are the things that can be done with an ordinary computer. They also think that the things that you can do on a Turing machine are exactly the things that can be done algorithmically. So say that something can be done algorithmically. If there is a finite set of instructions such that everything that needs to be done is encoded in the instructions. So if someone was to implement the procedure, if a person or a machine or whatever was to implement the procedure, they would require no creativity. So there would just be this process, and on each stage they would say, well, what do I need to do next? And like they look at the instructions, and they do exactly that, and the outcome is totally determined. So the idea is that anything that can be done at all in that way, anything that can be done algorithmically, can also be done with a Turing machine. So the theory of Turing machines, if that hypothesis is true, is just the theory of what can be done algorithmically, or what can be done by a finite being using a fully specified procedure. Now, it would be awesome to prove that result. The problem is that in order to prove it, you would need a formal definition of algorithmic procedure, and nobody has one. So I fear that that hypothesis will remain forever a hypothesis. It's sometimes referred to as the Church-Turing thesis. Okay, so let's get familiar with Turing machines. So there are all sorts of simulators on the web. Some are designed to make it easy to program things on Turing machines, which, in my opinion, defeats the point, because if you really want to program something, like, you shouldn't be using a Turing machine. So the one that I'm going to ask you to use for your problem set, and the one I'm going to ask you to use here, is like the most bare bones of all that I could find. It's also the most stable of all that I can find. So, all it is here you have your tape, and it's infinite in both directions. And then over here, you can, do people see where I am? Over here, you can put in an input, any input you want. So for example, A23. Will that do it? Yeah. And the reader is positioned where the square is, and that tells you what the current state is. And then what you do is that in here, you just write down instructions, just like that. Oh, by the way, this is important, and I failed to say it earlier. So when does a Turing machine stop? It stops when the command line it's working with asks it to go to a state that doesn't exist. So for example, this machine has states from 0 to 6. So it has 7 states. If you were to send it to state 17, then it would stop. But in order for it to be easier for humans to understand the code, often there's like this made-up state called halt. And then the convention is that no command line will start with halt. So when you reach this line of code and it asks you to go to state halt, so you just halt. OK, so why don't we do a little exercise? So for example, who can do this? Who can tell me how to design a Turing machine which starts with an empty tape and just goes right forever?
Let's see. So you should be able to do a line that's just 0 and then underscore for no character, right? And then new symbol. I don't know. You could put whatever you want there. And then direction, right or left, whichever way you want to go. And then new state 0.
Excellent. That's right. So if you're in state 0 and find a blank, then leave a blank, go right, and remain in state 0. So then if we just run it, our reader is just going to move to the right and do so forever. You had a question? Oh, no, sorry. OK, now suppose that you didn't know what was on the tape. So maybe your tape is like this weird sequence of blanks and ones. Then that might get stuck because it only works with blanks. So one thing you could do is just prepare it by saying, if you see a 1, then leave a 1 and go right and stay in state 0. Yeah?
Can you use a star?
Yes, you can. So let me first illustrate how it works like this, and then I'll introduce the star. OK, so in this case, then it is going to be able to go through the ones. But then, as you pointed out, it actually Okay, I was pretending to be an incredible purist and like using only the simplest possible machine, but even I have weaknesses. So I'm happy to go along with this simulator, which allows one to write this. So if you're in state 0 and you find anything you want, then I can't remember if you can say leave that thing. Let me, in this case, just say write an X and go right and stay in state 0. So let's see what this does. So here it just keeps going and replaces whatever it finds with an X. I wonder what happens if you add a star here. Oh, it just leaves whatever it found. OK, so there are some compromises. OK, so let's try something a little bit harder. So can anyone tell me how to program a machine that does the following? So you start with a sequence of ones of unknown length. And then what it does is just adds a 1 to the very end of that sequence and stops. And it should not be someone who's already spoken.
So you can start in state 0, and if you read a 1, just put a 1 and go to the right. And then stay in state 0. And then your next line is, if you're in state 0 and you see a blank line, then put a 1, go to the right, or it doesn't matter where you go, and press halt.
Excellent. Well done. So let's do it. So it just goes right, until it finds a blank, and then it writes a 1 and stops. Well done. OK. Shall I ask you guys to do? OK, let's do one more. So what about a program that takes a string and doubles it in length? So a string of ones, and you want it to have the tape end up with twice that many ones, and halt. And I'm perfectly OK to take partial suggestions. So for example, one thing someone could do is they could propose a plan, so just like how the machine is to work, and then we could collectively try to implement the plan. Yes?
So the general strategy is to have your state be your count, and then if you read a 1, then your state will go up, and you'll traverse to the right. And then if you traverse to the right and then you get a blank, then your state will go down by 1. And then you can keep decrementing and incrementing.
Nice. Oh, wait. Good. I love that. I think that's a super elegant thing to do. But I foresee a limitation. So that is definitely going to work if we know in advance how long our input is going to be. So if you know in advance that the input is going to be like 7 ones, then that's definitely going to work because you know in advance how many states you're going to have to work with. But so you're right, that works. But let me ask for a more difficult challenge. So let's have a program that works regardless of how long the initial string is. So like it could be a Google once, and we still want our machine to duplicate the number. That was very clever. So again, maybe the first step is for someone to propose a plan.
So we could go along our string of ones and start writing arbitrary numbers over top of them. So go 1, 2, 3, 4, 5. And then once we hit a blank space, we can write our ones and then go back through and fix everything back to a 1. So once we get to the end, just 1 all the way back.
I certainly like that. So I think that the trick, so our early, good. So we need some sort of counter to keep track of what's going on. And the earlier plan was to use states as counters. But of course, the problem is that we're only allowed to have finitely many states. So the new plan is to use the ones on the tape as counters. And an advantage of that is that the tape can be arbitrarily long, so we don't face that limitation. So here's one thing we could do. We could what we do is we have a machine start at the beginning, and then if it finds, oh good, okay, I know what to do. So first it puts a mark at the end of that, so that it knows where the original sequence ends. And then what it does is it goes back and replaces that first one by some kind of arbitrary symbol. And then it goes after its special mark and writes a 1. And then it goes back until it finds the arbitrary symbol. And it replaces the next one with another symbol of that kind. And it goes back and writes a 1. And so forth until it runs out of ones before the dividing mark. And then it comes back and cleans up. So what it does is it shifts back the original ones into ones, and it does something to get rid of the weird marker. Can people see what that plan would consist in? OK. So can anyone just start us off with a little routine that all it does is it goes to the end of its string of ones and say it writes down an X? Yes?
Can I propose an alternative without having to use like an end marker?
Of course, of course.
If we use like a 2 to represent like a 1 that hasn't been like replicated at the end yet, so we in an initial pass we can write everything over with the 2 to say we haven't replicated them yet. Then we go back until we like find the first 2, and then after we've gone to the blank space, we go back forward until we find the first blank space or like a 1, and then once we do that, we go back and find that first 2 in our list. And then we convert it to a 1, go all the way forward back, replicate that 1, and then repeat back to find that, again, 2, and then repeat. So we don't have to use that special marker and ignore the cleanup.
That's much more elegant because that cleaning was going to be pretty painful at the end. Yeah, I agree. That's much better. In fact, there's 2 versions of the plan you proposed. The first is one in which you just first switch all your original ones as 2s. The second one is in which you just consider them switched already, and the new things you write are 2s. And then, like, once you're done with that, then you clean up those 2s to turn them into 1s. Very nice. Very nice, very nice. OK, so why don't we, just for fun, why don't we use the version that you proposed? So we're going to, our first step is to just turn all those 1s into 2s. So who can propose a way of doing that?
So the directions are supposed to be such that any place you're at on the tape, you know what to do, right? So it doesn't. We're not assuming that you're like at the beginning of the tape when you start. So these should be directions that will get you to the beginning of the tape from wherever you are.
That is a very nice point. So in posing the challenge, I did not clarify how to do it. I agree. So I think really there's like an easier case and a harder case. So the easier case is assume that you're given a string of 1s and you're at the beginning. And the harder one is assume that there's a string of 1s somewhere. You need to go find it and then put yourself at the beginning. And that would be rough because you wouldn't know if you're left or right of the string of 1s. So I think maybe in the harder version, what you would have to do is you would have to somehow start going left and right until you found it. So let me propose that we start with the easier case. In fact, let me suggest that we only do the easier case, in which the challenge is simply to assume that you start at the beginning of a string of 1s. And what we need to do is make sure that we end up with twice that many 1s and a halted machine. Good. Thank you, Rose. OK, so can anyone propose a method for just turning all those 1s into 2s?
One, 2, right?
OK. So 0, 1, 2, right. And we stay in 0?
Yes.
Right, because the first thing to remember is the state. And we always start in state 0. So that's going to do. OK. That was easy enough. Okay, so can we go back to our master plan and just figure out what's next?
Usually I have trouble doing these without like actually drawing out like what's happening. Yeah. So like I usually like to like write out everything before I like try to dive in and type it in.
No, that is a good idea. That's what you guys should do. But I, of course, cannot do it here. Okay, so why don't we just start why don't we just enter a new state where what it's going to do is it's going to start writing. In fact, this is probably not maximally elegant, but just so there's no confusion, one that just starts writing threes, 1, 3 for each 2. And then we'll come back into a cleanup. So what it's going to do is it's going to write a 3 and then go back and put a 1 for the first 2. And then go back and write a 3 and then put a 1 for the second 2. And then so forth until it runs out of 2s. And then we'll have a bunch of 1s and a bunch of 3s. And then we go back and clean up the 1s. I'm sure there's a more elegant way of doing it, but that's, yeah, do you have a?
So I think we'll need 2 more additional states. We have state 1, which
3 states total?
Yeah.
Oh, that'll be so beautiful. Okay.
Yeah. So for the first state, for state 1, we're gonna keep going left until we hit either a 1 or a blank, and then if we do, then once we hit a 1 or once we hit a 1, okay, actually, yeah, then we go right, and then replace the next 1 with. Actually, hold on, never mind. Maybe this might not work.
Why don't we do this? Why don't I try my clunky method, which like is surely not going to be very elegant, but we'll get through it. And then at the same time, see if you can think of a more elegant way to do it. And then we'll implement yours if you can. Okay, so my super clunky method is just going to say, okay, so once you hit a 1, so once you hit a blank, so you're still in state 0, and once you hit a blank, write down a 3 and go left and enter state 1. So far all it does is it keeps going until it finds a blank, writes a 3, and starts its quest to the back. And then when you're in state 1, what you do is you keep going until you find either a blank or a 1. So let's first do it for a blank. So if you find a 2, leave the 2.
Left.
Yes, good. And no. I am very bad at this, so you should definitely intervene. So it keeps going until, that's just, it keeps going until it finds a blank. And then just leaves the blank and goes right. Okay, goes into state 2. So this is all it does so far. Right, so it does 2s, finds a blank, writes a 3, keeps going back, finds a blank, returns, and now it's ready to turn that 2 into a 1. So if you're in state 2 and see a 2, turn it into a 1, and then right, and we're going to enter. Oh, no, because I want it to be my counter. If you stayed in state 2, then you would just switch the 1s around. You would put a 1 instead of each 2.
Oh, yeah, you're staying in state 0. Yeah. I mean, you go back to state 0.
I think I'm going to need a new state. So I'm sure that this is not the most elegant to do it, but like for my clunky way, I'm going to need a new state.
Like a start state, 2 states to be the recursive state, and then a final state.
Exactly. That's how I'm thinking of it. I'm thinking like a clunky version of that. Yeah. So it just keeps going to the end, writes a 3, keeps going back, comes back, and then what it does there is that's like saying check. Okay, so I've dealt with my first 2, and I used it to write a 3 at the end. And now we're going to repeat that. Okay, so state 3 is you're repeating that. So in other words, you go to the end until you find a blank, and you return. So I think I need a volunteer. So can someone just tell me what to add to this for it to say, go forward until you find blank and write a 3 in that blank.
So instead of, wait, so current state's going to be a 2, current symbol's a, right? Oh, yeah, but the symbol, so you're going to have it go through all of the 2s until it finds a 3 or a blank? Is that what it is?
I think until it finds a blank.
Until it finds a blank. Okay, so then iterate through all of the 2s and all of the 3s. This is going to need to be 2 parts. So you're going to need 3, 2. What is the next? The next one's the new symbol's 2, so it won't change. Write state 3. And then the next one will be 3, 3, blank? No. 3, yeah. 3, write 3. And then the next one's going to be the blank that you add. Or, yeah.
Okay, so you find a blank, and then you add a 3, and then you go left, and then state 1. Okay.
We just need to do something, do a line that starts with 1, 3, which we haven't done yet.
Oh, yeah. Okay. Why not? So I agree. We need to do something. Why don't we just see what happens now, just to like get a sense of how it goes wrong when the recursion finishes. Okay. So let's see what's going on now. Okay. So it starts running, and then we put in a 3 and come back, check, and then put in another 3. Oh, that's what you were saying. Okay, so no rule for state 1, symbol 3. That's right. So if it finds, I'm going to put it here. If it finds a 3, it keeps the 3 and keeps going. Okay. Writes down a 3, check. Writes down a 3. Okay. So far, so good. Okay, so yeah.
I think that you need to just do the same thing you did for blank. So it should be 1, 1, 1, write 2.
I think you're right. Okay. So it keeps going. 3, check. 3, check. 3, very exciting. Check. 3, check. 3, check. And now what's going to happen when we run out of 2s? Check. 3, check. 3, check. Okay, so I think what we really need to do is we need to get it to switch to the termination state.
So at this point, it looks like we can just say, if we're in state 2 on a symbol 3, then, well, I suppose we want to turn it into a 1.
Okay, so we're cleaning up. We're starting to clean up. Excellent.
And then write, and then let's make a cleaning state 4, I guess.
Oh, thank God. Okay, thank God. This is good because it means that we've managed to end a recursion gracefully, and we're going to be able to escape. Okay, so now 4 is our cleanup. So then what we do is we find 3s and turn them into 1s, and keep going right, and stay in state 4. Yes, and of course, and we turn it into a space, which is fine because it was an extra thing. So we keep going, state 4, until we find a blank, and then we leave it a blank, and we go left and go to state 5. So this is an inelegance, but that's OK. And then 5, if it sees a 3, it just turns it into a...
It won't be a 3 at that point.
Make it a star.
Oh, make it a...
Or a 1.
It'll be a 1.
Oh, of course, it'll be a 1. It'll be a 1, of course, yes. Find a 1, then just erase it and do whatever you want. And
Can't you just do 4 with a rule for 1?
oh, nice. Oh, much more elegant. OK. So let's see what happens. I'm going to shorten the initial state to make it faster. OK. So we go, find our first 3, check. Second 3, check. Third 3, check. Fourth 3, check. Another 3, check. That's our extra 3 at the end. OK, now we're going to see if we manage to enter our magical state 4. Yes! So we clean up, get to the end, come back, and then Rose's trick. We erase that 1, and we're done. Yes! And I take it works, right? So we entered 5, and there's 10. Good. Yes?
I have a solution with 3 states and 6 instructions. If you
I'm so pleased about that. So my next thing I was going to ask is, can anyone do it in 3 states? But you're ahead of me. OK. So do you want to tell me what they are? OK. You're going to just erase this. OK.
So the first one is 0, 1, 2, right 0. Second one is 0, blank, blank, left 1. Third one is 1, 2, 1, right 2. And then 1, 1, 1, left 1. 2 blank, 1 left 1. 1 left 1. And then 2, 1, 1, right 2.
Oh my God. I bet this is as elegant as can be. So,
You need a space.
oh,
It halts at the beginning, if that's OK.
2, 1, 1. Oh, you mean I need a space there? Yeah. Oh, thank you. Good. OK, so shall I walk through it, and you can basically tell us what it's doing?
Sure.
OK, so reset. OK, so it's chugging along, writing 2s. Oh, I see what it's doing. Oh, this is much more elegant than mine. Yeah, I love it. Yes, surely this is the way to do it. Beautiful. Very, very nice. OK. So now you guys have a general idea about how to do things with Turing machines. This example is elegant in many ways. And one way in which it's elegant is that it used not just very few states, but very few symbols. So it relied only on having blanks and 1s, which is inevitable. So if you don't have at least blanks and 1s, then you can't do anything. And it had 1 auxiliary symbol 2. My machine was worse than that because it had the auxiliary symbol 2 and the auxiliary symbol 3. So here's a question for you guys. What is the least number of symbols you can have and still get your machine to do whatever you want it to do?
Two, because you can express each symbol as sort of like a binary representation and just have more states to process each like set.
Oh, that's so beautiful. Yes, 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 yes. That's exactly right. So you can think of it this way. You just start by saying to your programmer, OK, how many symbols do you really want? Do you want to have 3? Do you want to have 5? Like, how many do you want? And then what you do is you code each of the symbols they want. Say they want 5. So A, B, C, D, E. You just code each of them as a certain sequence of blanks and ones. So maybe you code that one like that, and 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 that one like that. And then, as you said, what you do is that whenever you would ordinarily use one command line, you need a bunch of command lines to work together to like digest the triple that's on the tape and corresponds to each of your symbols. Yes?
Do you no longer care about how many states you're using? Because then can you just do it in unary?
So I'm thinking of blanks and ones as unary. Because like true unary would be you only have blanks.
And basically your states are just like counting up how many blanks you've seen or something.
Well, but the problem is that if it's really all blanks, then like there's nothing to count. So the reason I'm being confusing. So the reason I'm being confusing is that there's two ways of thinking of binary and unary. So the first way of thinking of it is that you have blanks. Of course you have blanks. And then you have two symbols, say 0 and 1. And the other way of thinking of binary is that you have blanks, and then that already counts, and then one additional symbol. The literature is mixed on that. So when you read about Turing machines, they sometimes think of it one way, and they sometimes think of it another. So let me just put it this way just for the sake of concreteness. So let's say that blanks don't count as symbols, in which case we can use your terminology and say that you can do everything you want using just one symbol, in addition to the blank, but one symbol. And of course, that makes programming even more painful, but it means that theorizing about Turing machines is even simpler. And that's something we're going to make use of next time. But I think that already you guys can use the tools from the previous weeks to answer the following question. Consider the set of all functions from natural numbers to natural numbers. So, for example, one such function is the one that assigns 0 to every natural number. Another such function is one that assigns n plus 1 to each n. Lots and lots of those. Is every one of those functions Turing computable? In the sense that you can program a Turing machine such that if you give it a sequence of n ones as input, it'll write down a sequence of f of n ones as output and halt. So the question is, can every function from natural numbers to natural numbers be computed in a Turing machine in that sense?
No, the Turing machines are countable.
Yes, exactly. Exactly. The Turing machines are countable because Turing machine programs have to be finite. But of course, those guys are uncountable. There are as many such functions as there are real numbers. So as you pointed out, there have to be functions from natural numbers to natural numbers that are not Turing computable. And what we're going to do next time is we're going to see some very, very cool examples. And we're going to prove that they're not Turing computable.